Hello everyone, my name is Kalita Prema and I'll be presenting renal physiology today. So the summary of body fluids, the total body water is approximately 60% of the body weight and it is higher in newborns and in adult males and lower in adult females and individuals with more adipose tissue. So the distribution of water is as follows. Intracellular fluid makes up at least 2/3 of the total body water. Major cations are potassium and the magnesium, and major anions are proteins and organic phosphates like ATP, ADP, and AMP. The extracellular fluid makes up about the 1/3 of the total body water, which is composing of plasma and interstitial fluid. And the major cations are sodium, major anions are chloride and bicarbonate, and plasma is about 1/3 of the extracellular fluid, which contains proteins like albumin and globulins, and interstitial fluid is 3/4 of the extracellular fluid, similar to plasma but has little protein. The 60-40-20 rule is signifying that 60% of the total body weight is total body water, and it is 40% of the intracellular fluid and 20% in extracellular fluid. Now, measuring the fluid volumes, the dilution method is used to measure the fluid compartment by volumes, introducing a known substance, which is measuring its distribution. Like titrated water is used for total body water, mannitol is used for extracellular fluid, and Evans blue is used for plasma volume. A summary of water shifts between compartments consists of the basic principles. The osmolarity of the extracellular fluid and intracellular fluid must be equal and at steady state. The water shifts between compartments to maintain this osmotic balance, and solutes like sodium chloride and mannitol are confined to extracellular fluid and does not cross the cell membranes. Examples of water shifts are infusion of isotonic volume like sodium chloride. The extracellular fluid volume increases without a change in osmolarity. There is no water shift occurring between the extracellular and intracellular fluid, and plasma protein concentration and hematocrit increase due to dilution, and arterial blood pressure also increases due to increase in extracellular blood volume. Secondly, there is diarrhea, where there is isoosmotic volume contraction, where ECF volume decreases without any change in osmolarity, no shift between the extracellular and intracellular fluid. Plasma protein concentration and hematocrit increase, and arterial blood pressure decrease due to decreased extracellular fluid volume. Thirdly, there is excessive sodium chloride intake, and that is basically the hyperosmotic volume expansion, where ACF osmolarity increases due to added sodium chloride. Then we have number 4, the sweating in desert condition, where there is hyperosmotic volume contraction and the extracellular fluid osmolarity increases as sweat is hypotonic and loses more water than salt. ECF volume decreases, water shift happens, reducing ICF volume, and plasma protein concentration also increases. Hematocrit remains unchanged due to RBC shrinkage. Then we have SIADH, which is basically a hyperosmotic volume expansion, where ECF osmolarity decreases due to water retention. And lastly, we have the adrenocortical insufficiency or hypoosmotic volume contraction, where the ECF osmolarity decreases due to decreased NaCl reabsorption, which is the loss of sodium chloride, and extracellular volume decreases and water shifts to ICF, increasing the ICF volume. The plasma protein and concentration hematocrit increases as well, and arterial blood pressure decreases due to reduced ECF volume. Then we go to the summary of renal clearance, renal blood flow, and glomerular filtration rate. Number 1, the renal clearance is basically, it represents the volume of plasma cleared of a substance per unit of time. Volume is C is equal to UV by P, where C represents the clearance, U urine concentration, the V is the urine flow rate, and P is the plasma concentration. Then we have the renal blood flow, where the overview is that the renal blood flow is 25% of the cardiac output. The key regulation factors for this is vasoconstriction and vasodilation. And thirdly, the autoregulation of the RBF, basically the renal blood flow, is the purpose keeps the renal blood flow constant despite changes in the arterial pressure, and there are mechanisms like myogenic mechanism, and then there is tubuloglomerular feedback as well. Before, the measurement of renal plasma flow is basically the substance used is para-amino hypuric acid, where there is the renal blood flow is calculated using the clearance of para-amino hypuric acid, which is filtered, secreted by the renal tubules, and its clearance reflects the renal blood plasma flow but underestimates the true plasma flow by approximately 10%. And we have measurement of renal blood flow, which is calculated by the renal plasma flow divided by 1 minus hematocrit. Then we move on to the glomerular filtration rate, which is measured by inulin clearance. Inulin is used to measure the GFR, which is basically filtered by the glomerulus by neither absorbed or nor secreted. It is the calculated formula is the glomerular filtration rate is equal to U inulin into the V by P inulin, which is basically the inulin concentration in urine into the urine flow rate divided by the inulin concentration in plasma. Then we have the estimating the glomerular filtration rate with BUN and serum creatinine. Both the BUN or the blood urea nitrogen and serum creatinine rises when the glomerular filtration rate decreases. In pre-renal azotemia, which is a low blood volume, the BUN increases more than serum creatinine, resulting in elevated BUN by creatinine ratio, which is more than 20:1. The glomerular filtration rate also decreases or declines with age, but serum creatinine levels often remain stable due to decreased muscle mass. Then we have filtration fraction, which is a fraction of renal plasma flow that is filtered across the glomerulus, which is GFR by RP. And normally the filtration fraction is about 0.20, meaning 20% of the RPF or the renal plasma flow is filtered. An increased FF of filtration fraction enhances the protein concentration in peritubular capillaries, which is promoting reabsorption. Determining the glomerular filtration rate is done by the Starling forces, which is driven by the net ultrafiltration pressure across the glomerular capillaries, which is calculated using the Starling equation, which is given as follows. Now, there are also changes in the Starling forces, like alterations in the glomerular capillary pressure, Bowman space pressure, or oncotic pressure, can also affect the glomerular filtration rate and the filtration fraction. The summary is that of the resorption and secretion in the kidneys is that the calculation of resorption and secretion rates are done by resorption rate is filtered load minus the excretion rate. The secretion rate is calculated by excretion rate minus the filtered load. Then the filtered load is actually calculated by the glomerular filtration rate into plasma concentration, and then excretion rate by V into the which is the urine flow rate into urine. Then we have the transport mechanisms for glucose. There is filtered load, which is proportional to plasma glucose concentration, reabsorption occurring via the sodium glucose co-transport in the proximal tubule. Then we have the excretion where there is glucose begins to appear in the urine, where plasma glucose exceeds 250 mg per deciliter with significant excretion above 350 mg per deciliter. Then we have TM for para-amino hypuric acid, where there is filtered load, secretion and excretion happening, where the filtered load increases proportionally with plasma with para-amino hypuric acid concentration. Then there is excretion, which is excreted into the urine, and there is also excretion rate is combination of the filtration and the secretion. The relative clearance of substances is the highest clearance happens with para-amino hypuric acid substances that is filtered and secreted have the highest clearance. Lowest clearance are of proteins and are reabsorbed like glucose have the lowest clearance, and the clearance which is equal to the glomerular filtration rate are substances like inulin, which are then filtered but not reabsorbed or secreted by the clearances which is equal to it. Now there are non-ionic diffusion as well, where there is weak acids like excretion depending upon the urine pH. At acidic pH, the non-ionized form predominates and can go back, diffuse and reduce secretion. But weak acid bases like the alkaline pH, the non-ionized form and predominates and can get back and diffuse, reducing excretion. This framework basically illustrates the balance between the filtration, reabsorption and secretion, which transport maximum determining which substance start appearing in the urine. Now the summary of the sodium chloride regulation in the nephron, where there is a single nephron terminology, is basically tubular fluid, urine at any point along the nephron, which has a ratio, compares the concentration of a substance in the tubular fluid to plasma. When there is tubular fluid divided by plasma is equal to 1, there is no reabsorption or no reabsorption proportional to water. When it is less than 1, more reabsorption has happened of the substance than water, and when the ratio is more than 1, it is less of the reabsorption of the substance secreted into the tubule. Then there is also sodium reabsorption overview, where the sodium ion is freely filtered across the glomerulus, with the most of it being reabsorbed along with the nephron, and less than 1% excreted in the urine. Then sodium reabsorption along the nephron, where there is proximal tubule, more than reabsorbs 67% of the sodium and water isosmotically. Then early proximal tubule absorbs, where there is sodium is reabsorbed and bicarbonate, glucose, and amino acids via the co-transport. Late proximal tubule, the sodium reabsorbed with chloride, and glomerular tubular balance ensures a constant proportion of sodium which is reabsorbed despite changes in the glomerular filtration rate. Then in the thick ascending limb of the loop of Henle, there reabsorbs at least 25% of the sodium via the sodium-potassium chloride co-transport, impermeable to water, resulting in a dilution of the tubular fluid, where the ratio becomes less than 1. The distal tubule and collecting duct there together reabsorbs 8% of the sodium ion, and early distal tubule, the sodium is reabsorbed via the sodium chloride co-transporter site of thiazide diuretic action, and late distal tubule or the collecting duct, principal cells reabsorb sodium and water regulated by aldosterone and ADH, and A-intercalated cells, they secrete the hydrogen ions and reabsorb potassium ions. The summary of potassium regulation in the urine is that the shifts of the potassium between the intracellular and extracellular fluid, the potassium is primarily intracellular. Hyperkalemia is caused by the potassium shifting out of the cells. Hypokalemia is caused by potassium shifting into the cells, and potassium balance is achieved when urinary secretion or excretion equals to the dietary intake. The renal regulation of the potassium balance is basically when there is potassium excreted. It varies about 1% to 110% based on dietary potassium intake, aldosterone levels, and acid-base status. The glomerular capillaries, the freely filtered potassium ion, so the total filtration by the p ratio is about, for potassium imbalance space, which is 1.0. Proximal tubule reabsorbs about 67% of filtered potassium along with sodium and water. In the thick ascending limb of loop of Henle, it absorbs about 20% of the potassium via the sodium-potassium chloride co-transporter, and in distal tubule and collecting duct, alpha intercalated cells reabsorbs at least about potassium under the low potassium diet conditions, where the principal cells either reabsorbs or secrete potassium depending on the diet, aldosterone, acid-base status, and urine flow. The regulation by diuretics is basically when there is loop diuretics like furosemide, it inhibits the sodium-potassium chloride co-transport. Then thiazide diuretics basically block sodium chloride co-transport in the distal tubule, and potassium-sparing diuretics basically reduce the potassium secretion in the collecting duct. Now this summary basically outlines where there is a critical point of sodium and water reabsorption, highlighting the major segments of the nephron and the effects of hormonal and pharmaceutical regulation. Now the mechanisms of potassium secretion is basically when secretion of principal cells. In the principal cells, how it happens is basically potassium is actively transported into the cells by the potassium sodium pump, and then passively secreted into the tubular lumen through the potassium channels. The factors which are affecting the secretion are dietary potassium, like high diet in potassium increases potassium secretion and low diet decreases. Then aldosterone increases potassium secretion by raising the sodium ions entry into the cell, and potassium ions reuptake. That leads to hyperaldosteronism, which leads to hypokalemia. Then hypoaldosteronism leads to hyperkalemia. Then acid-base status also affecting acidosis leads to decrease in potassium secretion, and alkalosis increases the potassium secretion. Then diuretics like thiazide and loop diuretics increases the potassium secretion by increasing the flow rate, causing hypokalemia, and potassium sparing diuretics like spironolactone decreases the potassium secretion, preventing hypokalemia when used with other diuretics. Then luminal anions like increase potassium secretion also by making the lumen more negative. Now this summary basically covers the essential points of potassium regulation, including process of reabsorption and secretion, as well as the influence of the diet, hormones, and acid-base balance, and medications as well. So the urea, it is basically the 50% of the filtered urea is reabsorbed passively into the proximal tubule. ADH increases urea permeability in the inner medullary collecting ducts, which is aiding in urea recycling and corticocapillary osmotic gradient. Urea excretion depends upon the urine flow rate, more reabsorbed at low flow and rates and more excreted at high flow rates. Then phosphates, like 85% of the phosphate is reabsorbed in the proximal tubule via the sodium-potassium flow transport, and the parathyroid hormone inhibits the phosphate reabsorption in the proximal tubule, causing phosphaturia and increased urinary cyclic EMP. Then phosphate also acts as a urinary buffer for hydrogen ions. Calcium, now 60% of the plasma, which is calcium, is filtered mostly in 90% is reabsorbed in the proximal tubule and thick ascending loop of Henle through the sodium linked processes. The PTH of parathyroid hormone increases the sodium reabsorption in the distal tubule. Loop diuretics increases urinary calcium excretion, while thiazide diuretics decreases the calcium. Then magnesium is reabsorbed in the proximal tubule, thick ascending limb, and distal tubule. Calcium and magnesium compete for the reabsorption in the thick ascending limb, so the hypercalcemia increases magnesium excretion and vice versa. The concentration and dilution of urine basically happens by the regulation of plasma osmolarity, controlled by varying water excretion and relative to solutes affecting the urinary osmolarity. Concentrated urine, basically when there is ADH levels are high, dehydration or the condition SIADH, which urine becomes hyperosmotic and there is urine osmolarity more than blood. The corticocapillary osmotic gradient is established by the countercurrent multiplication and urea recycling maintained by the vasa recta, and ADH is basically increasing water reabsorption in the collecting ducts, leading to concentrated urine. We have diluted urine, which is basically a mechanism produced when ADH is low and resulting in hypoosmotic urine, and without ADH the water is reabsorbed in the collecting ducts, so the dilute urine when it is excreted. Then free water clearance is basically, it is measured by the kidney's ability to concentrate or dilute urine. Positive CH2O, basically it is indicating solute free water excretion, while negative CH2O is reflecting water reabsorption where there is concentrated urine and high ADH. So the urine types could be isoosmotic, hypoosmotic, and hyperosmotic as well. Then we have a brief summary of the acid-base balance, which is the acid production basically is a volatile acid carbon dioxide produced from the cellular metabolism, combines with water to form carbonic acid, which dissociates into hydrogen ion and bicarbonate. And then there is non-volatile, which is fixed acids, including sulfuric acid from protein metabolism and phosphoric acid, which is from phospholipid metabolism, as well as acids like lactic acid and keto acids in disease states. Number 2, there are buffers like extracellular buffers. The major buffer is bicarbonate, and phosphate is also an important for urinary buffer. And intracellular buffers like organic phosphates and proteins like hemoglobin buffer acids within the cells. There is also Henderson-Hasselbalch equation, where it is used to calculate the pH following the relationship between the acid and base, which is forming a buffer as well. Then we have renal acid-base regulation, bicarbonate reabsorption primarily occurring in the proximal tubule, increased carbon dioxide, which increases the bicarbonate reabsorption, compensating for respiratory acidosis. There is excretion of the hydrogen ion. So via titrable acid and ammonium, which helps eliminate fixed acids and generate new bicarbonate. Then acid-base disorders like metabolic acidosis is caused by excess fixed acids leading to decreased bicarbonate, and respiratory compensation also involve hyperventilation. Then there is metabolic alkalosis, where there is loss of fixed acid like vomiting happens, leading to an increase of bicarbonate, and respiratory compensation involving hypoventilation. Then there is respiratory acidosis, which is causing carbon dioxide retention like hyperventilation, leading to increased acid and hydrogen ion and bicarbonate, which is a renal compensation involving increased hydrogen ion excretion. Then there is respiratory alkalosis, which is caused by carbon dioxide loss, example the hyperventilation, leading to decreased hydrogen ion and bicarbonate and leading to renal compensation involving decreased hydrogen ion excretion. So this basically covers the basics of the acid-base regulation, buffering, and compensatory mechanisms. That is all from my side. Thank you so much for listening to this lecture.